Alright, so let's finish off the molecular orbital. Now we are doing we are going to study the molecular orbital of the homonuclear diatomics in the p block. And to do that, we are going to need energy of the molecular orbital. Actually, not the energy of the new molecular orbital. And just because that there will be the interference between the orbitals, and that actually changes the molecular orbital a little bit. So it's difficult to actually predict what molecular orbital is going to be lower in energies. So to actually do that, you really have to calculate the energy of the orbital by solving the Schrödinger equation. That's probably the best way to do, but it's not definitely not for this class. So the energy of the orbital is given like this in this particular class. So that's just for the p blocks. So now for the b orbital, b atoms, we have 2s, right? And then another 2s is maybe somewhere around here, right? And then 2p block is 2p, px, py, pz. Those are going to form the molecular orbital that looks like that. But for the s block, you are going to form a bonding sigma orbital and then anti-bonding sigma orbital. And then for the p block, we are going to form pi orbital from the bottom, and then sigma orbital, and then pi orbital, and then sigma orbital. I'm gonna put the name of the orbital or the symmetry of the orbital in each one of these guys. Remember that when you have a star, that means it's anti-bonding, right? So necessarily the energy is above the starting point. Everything else is lower than the starting point. And pi orbital is actually the mixture of the py and px. So py and px from the left b atom, and then py and px, that's why, from the right b atoms. So you have used 4 orbital, right? When you mix 4 orbitals, you are going to create 4 new orbital, which is pi and pi star. And if you actually mix up the pz and pz from the left b atom, and then pz from the right b atoms, you are going to create 2 new orbital, which is sigma and sigma star. And same goes with the 2s too, right? 2s, you create the sigma orbital and sigma orbital, and 2s and 2s, so input is 2 orbital. New molecular orbital is going to be 2 because you use 2 orbital to form 2 new orbitals. So let's just fill in the electrons for each one of these guys. That's a B, right? B. if you don't remember, it's a 2s squared 2p, right? So that's that, right? So I have 4 electrons to fill here because you have used 1, 2, 3, 4, and that 1, 2, 3, 4, right? Now, what about this guy right here? 1 and 2, right? That goes in right here. The next step is gonna be actually right here, and that's because of the combination of the off-bow principle and Fun's rule. Right, Fun's rule, you're gonna go with up, 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 and then down, 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 right? And then off-bow principle is the one that filling the electrons from the lowest energies, right? So that's pretty much what there is to it, all there is to it. All right, let's do the next one. So this time around it's a carbon. So similarly, we have a 2s orbital of the carbon and 2s orbital from the carbon. And let's just write it around here. And then 2p orbital, which is 1, 2, 3, and then 2p orbital, which is 1, 2, 3, px, py, pz, right? The s orbital always makes a sigma type bonding orbital, and then the non-bonding orbital, right? So it looks like this. And then the p orbital combinations is gonna produce pi bonding orbital, sigma bonding orbital, and then pi bonding orbital, and then sigma bonding orbital. So this is going to be pi, sigma, pi star, oops, and then sigma star, right? And then let's just fill in the electrons for each one of these guys. So you have that and that for the carbon. The carbon, if you recall, it's a 2s squared 2p squared, right? So it looks like this, right? Now s mixing, you have 4 electrons, right? So I'm gonna fill in the 4 electrons here, and then the 2p mixing, you have total of 4 electrons, right? So you're gonna go with up, up, down, down. That's it. So that's the C2. So there is no unpaired electrons for this particular carbon. Let's do the nitrogen. The procedure is pretty much the same. I think you already got the how you are supposed to do these things. So let me just do the 2s right here, and then 2p. You have 3 of these guys, and then 2p. You have 3 of these guys, and then s orbital is gonna have some sigma orbital, 2 of those guys, and then p orbital, according to this one, it's a pi always comes with the 2 boxes of the 2 orbital, sigma, and then pi star, and then sigma, right? So let me just put the pi, sigma, pi star, sigma star. Right. All right. So let's just fill in the electrons. P is N2, right? Nitrogen is a 2s, 2s, that's this. 2s squared, 2p3, right? So it look like this, right? So the S mixing, 2s mixing, you have 4 electrons in total, right? So there's nothing changed. But for the P mixing, you have 6 electrons, right? So 1, 2, 3, 4, 5, and 6. That's it. There's no unpaired electrons on this one either. Alright, let's do the oxygen. Oxygen again, it's 2s. I think you should probably be able to do these things without even looking at these things. So just 2s. I'm just gonna do it anyway. But 2p, you have 1, 2, 3, and then 2p, it's 1, 2, 3, and then s is gonna form sigma and sigma star, right? And then p orbital. Now check out this energy order. So sigma is gonna be the lowest for this one, and pi is gonna be following that, and then pi star follows that, and sigma star follows. So sigma, pi, pi star, star always above the starting energy, sigma star. Okay, so oxygen is 2s square 2p4, right? So it looks like this. 1, 2, that, right? Alright, so for the S mixing, you have 1, 2, 3, 4. There's nothing changed. And then we have total of 8 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8. Now we have 2 unpaired electrons in the pi star. Alright, then F2 atoms, F2 molecules. I'm getting tired. 2s, that, and then 2s, that, and then 2p. You got 1, 2, 3, 2p, 1, 2, 3, and it's the same as always. So, you have this s orbital, the new sigma and sigma star, and then I'm going to follow this order. Sigma at the bottom, pi next, followed by another pi star, and then sigma, right? So 6 orbital, you form 6 of these guys. 2 input, 2 output, right? Now for the F, you have 2s squared 2p5, right? So something like this. 1, 2, 3, 4, 5. Okay. So S mixing, you have 4 electrons. 1, 2, 1, 2. Alright, let's start the P mixing. You have 5 from here, 5 from here, it's 10. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's good. So there is no unpaired electrons. And neon, the last one. So 2s, you have that, 2s, you have that, and then 2p, 1, 2, 3, 2p, 1, 2, 3, and then as always, s orbital is gonna make the sigma and sigma star, and then for the p orbital, you're gonna have that order. So the sigma at the bottom, pi next, pi star next, and then sigma, right? And for the neon, you have 2s squared 2p6, right? So it's pretty much everything is filled, right? So for the s mixing, you have 4 electrons to fill, so that's that, right? And then for the p mixing, you have total of 12 electrons. So let's just fill in all of those guys. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, that's good. There's no unpaired electrons too on this one. Let's calculate the bond order for each one of these guys. Remember the bond order formula? The bond order formula is the number of electrons in the bonding, number of electron in bonding minus number of electron in antibonding divided by 2, right? So for this particular case, you have 2 electron in bonding orbital. I'm talking about these guys right here, and 0 here, right? So 2 minus 0 divided by 2. So the B2 atom actually have single bond. Let's do the carbon. So the bond order is the number of electron in bonding minus number of electron in antibonding divided by 2, right? So for this particular case, we have 1, 2, 3, 4 in the bonding orbital, and then 0 in antibonding, right? So 4 minus 0 divided by 2 is 2. So this is a double bond. That's more or less what I expected, but let's do the nitrogen. Nitrogen having the 6 electrons in bonding, 0 in antibonding, divided by 2, 3. So nitrogen is actually triple bond. And if you recall the list of structures, they look like this, and it is consistent, right? Triple bond right here. And let's go back to the carbon for that matter. 1, 2, 3, 4. 1, 2, 3, 4. Right, so these 4. So that one is gonna be single bond. And then it's really in order for this one to actually satisfy the octet rule, you really have to form the quadruple bond. That doesn't happen, right? It's you really have to have 1, 2, 3, 4 bond. But yeah, Lewis dot structure doesn't work for this one. Same goes with actually B2. Like B right here, you have 1, 2, 3 dot, right? And B right here, you have 1, 2, 3. So maybe that, but it doesn't matter. It doesn't work, right? So yeah, for the Lewis dot structures, it works for the most of the time, but there are so many cases that it doesn't work. Just nitrogen actually works perfectly fine, right? Alright, then do the oxygen. Let's go back to the bond order. So the oxygen, you have 6 electrons in a bonding orbital. What I meant to say is the 6 electrons in bonding orbital, and then 2 in anti-bonding, right? So 6 minus 2 divided by 2. Voila, that's 2 bonds, so it's a double bond. And if you do the Lewis dot structures, you actually should get this. Oops, that's supposed to be 2 dot right here. Right, it's consistent with that 2 and that 2 is same stuff. So it's another case that the Lewis dot structure works, but the molecular orbital always works. And if you actually notice that this particular case, you have this not unpaired electrons, right? And because of this, oxygen is actually react to the magnet. They have this magnetic properties. So the yeah, you should probably watch some videos on the oxygen reacting with a strong magnet. I give you a link to that. Alright, then the next one is the F2. So for this bond order, you have total of 6 electrons in the bonding orbital, and then 4 electrons in anti-bonding. So 6 minus 4 divided by 2 is 1, right? So that's a single bond. And what do you know? It's the if you do the Lewis dot structures, you should get a single bond. So that's that. Another case that Lewis dot structure works, and the molecular orbital always works. And for the neon, you shouldn't expect neon to have the dimers, right? Because the neon itself is already having this full octet satisfied. So for this particular case, we have 6 electrons in bonding orbital, and then 6 electrons in anti-bonding. So you know where I'm going. 6 minus 6 divided by 2, which is 0. So there is a 0 chemical bond, and because of that, neon dimer doesn't form. So according to this particular diagram, I think that's probably good enough.